ahead and start recording. Okay, I did look at the surveys, and I have a couple things I want to report. First of all, it seems that integrals beat matrices 9-5, so we'll be doing mostly integral math. I was actually surprised there were 5 people that wanted to look at matrices. So I'll probably do a little bit of matrix work as well. We'll try to talk about both perspectives, but I'll focus more on the calculus, given your vote. I think that's a good enough reason to try to talk a little bit about both. Another thing that I found very interesting were your movie choices, which is always the most interesting thing of them all. And I was able to actually, so many people added their movies, and I decided that we can make a canon of CHEM 3332 movies. And it's actually a very diverse list. I just wanted to write it down because I think it's kind of fun. The first result was Shawshank Redemption. So if anyone's never seen that, that's actually a great movie, a great recommendation. I might as well add mine. So this is the quantum canon. Shawshank Redemption. Mine is Blade Runner, is my favorite movie of all time. So let's put that there. I might as well get a choice.
Which cut do you like?
Good question. Director's cut. I also like Final Cut. I find theatrical to be completely unwatchable due to the narration. I hate the ending of it too. The director's cut's great though. I do like the Final Cut as well. They're both good. I also like the other one, the sequel too, quite a bit, but not as much. Someone recommended this one, and I thought this was great, Grand Budapest Hotel. If you've never seen this movie, I highly recommend it. It's really fantastic. There's another movie by Wes Anderson called Moonrise Kingdom that came out right before this. That's also awesome, especially relevant to me. It was my first date with my wife, so it's extra good. I've got to add Twilight here, of course, for all the Twilight fans. Someone suggested, I thought this was an interesting one, World War Z, which is not the zombie movie I would choose, but an interesting choice. The classic, The Good, the Bad, and the Ugly. Great choice. Unforgiven I like more, but they're both great movies when it comes to Clint Eastwood. Both are great. This one's also fantastic, 10 Things I Hated About You. I've seen that movie about 100 times. Mostly because of my wife. Another one, I don't know if you've ever seen this one. This is a kind of recent movie, Call Me By Your Name. It's a good one with Timothy Chalamet. And a very, very creepy Armie Hammer. The Conjuring. Which Conjuring was it, Carolyn? You prefer?
I like all of them.
You like all of them?
I haven't watched the more recent ones recently, so.
I'm sorry?
I haven't watched the more recent ones recently, so.
Oh, okay. Yeah, I don't care for the third one too much, but the first two are pretty good. I like that one. Another great movie that someone suggested was Freedom Writers. With I think Hilary Swank's in that movie, and that's a really good one. Same person suggested. I have a feeling maybe a lot of people in criminal justice and like this movie too, or anybody in forensics, law-abiding citizen. That's a fun one. And the final one was Big Hero 6. So there's our canon. I guess those are the greatest movies of all time, and I'm pretty happy with that list. It's actually a pretty good list, all over the place. Someone else suggested Lion King too, but they had like 4 movies on their list, so I only picked 2. One more thing is most of you, or a good chunk of you, suggested you'd like to learn a little bit about subatomic particles, which I am very happy you did. I think there were probably 8 or 9 of you that said something to that effect. And so I decided today, let's talk about subatomic particles. This is a perfect time to talk about the structure of matter. Because what it'll do, we can talk about it at the end too, right? Once we've learned some theory and stuff, we can talk about how it fits into the world, what we've learned this semester. But instead, I like to flip it around, right? Let's actually look at the answer, right? What does the universe look like? And see where our class fits into the big scale of all the things that make up the universe. And I think that's a really great way to start the perspective. None of this is testable material, but I think this is more of just a discussion. And of course, I'll take your questions too. I can't do particles and subatomic particles justice in one day. It just doesn't work out. It's really something you have to. It takes a long time to learn and to really appreciate. But I can give you the basics. You talk about the individual types of particles. What are atoms made out of? What are the differences between types of particles, and how do we identify them? And also, what are the unifying themes behind all of them? There's the concept of a fundamental force. And certain particles interact between different forces. Some have electrical forces, things with charge, some don't. And so I think it's reasonable to talk about these things today. And then what we can do is we can pin down exactly where we're going to be sitting this semester, right? We'll have a very clear idea about where chemistry is in the grand scheme of the universe. And so I think the best way to start is to first talk about the ways that matter can interact with itself. The fundamental forces. All right. Does anyone know? There are 4 of them. Does anyone know what they are? Any guesses? What's the fundamental force keeping us on the ground? Gravity. All right, so I'm going to call it gravity. What force pulls an electron and a proton together? Electromagnetic. Does anyone know the other 2? What keeps protons together from falling apart? Does anyone know the answer to that? This is the force that keeps a nucleus together. It's called the strong force. And there's another one that also is a nuclear attraction called the weak force. Right? All of the physics we know and understand, all the interactions in the world can be, well, as far as that we know, can be put together, put into one of these 4 forces. Okay? Some things interact one way and some don't the other way. For instance, large masses like you and I, we interact with the Earth with gravity, but we have a very poor interaction electromagnetically to the Earth. Right? And strong and weak don't even apply to us. So sometimes these forces can interact together. Some particles interact in multiple ways. Some interact in only one. And it depends on their size. It depends on the energy you're looking at and the scale of the interaction. How close are they together? And they also have different strengths. Some are stronger than others. So often the way that we measure strength of a force is we measure what's called the coupling constant. By measuring a number, just a number, what we call a coupling constant. Right? And this tells you roughly how strong the force between 2 particles are, given a force. Okay? Each force has its own coupling constant. So I can make a list here. Here's our forces. Make a table. And we'll put coupling constant here. And another thing, so when we have a force, we can specify how strong it is by measuring its coupling constant. It's just a number. Smaller the number, the weaker the force is. And we also need something that carries the force, right? You need something that moves energy from one place to another that moves the force, right? You have to have something that moves it, right? Gravity in some ways is kind of this idea of having 2 masses next to each other. They naturally attract each other. And the way that Einstein says that they move force is that you're moving energy through space-time. Right? That's a very complicated way of saying it. But each of these forces have some sort of carrier, a particle even. What we call these a force carrier or a particle. Each of them have a particle associated with them that carries the force from one system to another. Right? How do you move this? How do you move this energy from one thing to another? So let's talk about the coupling constants here. So we can measure the coupling constants any way we want, but the way that physics usually does it is relative to the strongest. So we take the strongest force and assign it a coupling constant of 1. So of course, by name, the strongest force is the strong force. It has a strength of 1. The electromagnetic force turns out to have a strength of 1 over 137, which is about 0.0073. This number is known to about 12 significant digits very accurately. But it's roughly 1 over 137. It's kind of a coincidence. 1 over 137 gets you like 7 significant digits or something like that. It's very, very close to that fraction. So it's weaker than a strong force. But compared to gravity, gravity has a coupling constant of 10 to the minus 39 on this scale. 40 orders of magnitude weaker. 37 orders of magnitude weaker than the electromagnetic force. Okay, gravity is very, very weak. That's why you only can observe its effects on very, very large systems, right? Very, very large particles. Planets, stars, very large forces. You have to have a big mass for gravity to exhibit a large force. And then, of course, there's the weak force, and that's the last one, that's 10 to the minus 6. It's about 1 million of the force. So the weak force is still stronger than gravity, but it's much weaker than the other two. And each of them are associated with a carrier, some particle that transmits this energy from one place to another. Gravity, we have no idea. There's no idea what the carrier of this is. All we see with gravity is that you have two masses, and if they're heavy enough, you use Einstein's equations, and you can see how gravity happens. Because it's very complicated, right? So gravity, we really don't have a really good microscopic description of. There's no microscopic description of gravity. We just know two masses, they warp space-time, and that causes space to curve, and that causes gravity. The electromagnetic force is carried by something that we observe every day, a photon. Light is what transmits the energy and the force of the electromagnetic field. Right? The photon, in some ways, electricity and light are exactly the same thing. Right? You think of electricity as a transmission, right? You have electrons moving through a wire, right? A current of electrons, right? Like in electrochemistry. But the force, the electromagnetic force, the attraction between two electrons in that flow, right, to keep them together and keep them flowing, that repulsive force or the attractive force between a positive and negative charge, that's transmitted by light, a photon. Right? Electrons interact with each other by transmitting photons between each other. Right? That's how they move that force around. Right? The photon is the force carrier for electromagnetism. So anything about light, when you think about light, you think about electromagnetism, right? That's Maxwell. The strong force is carried by something called a gluon. We'll talk a little bit about gluons. We won't really talk about gluons, but we'll talk about the things that gluons hold together. Right? The strong force is what holds a proton together and what holds a neutron together and what holds a nucleus together, in fact, as well. Right? The strong force, that's what glues things together, hence the name gluon. And the weak force is mediated by two very large, very unstable particles that you've never heard of, called the W and Z bosons. Not very important, but I'll explain why they're very important very soon. Okay, these are very, very unstable particles. You can really only see them in particle accelerators. And that's why the weak force is so weak, is because their particles are very massive, very unstable. It's not a particularly efficient force. Transmission is very difficult. So the weak force is quite weak. And so for instance, of course, the photon's been known for a very long time. We've known light for a long time. Gluons weren't discovered until about the 1960s, and W and Z bosons weren't observed until the 1970s. Okay, so in fact, the physicists came up with these ideas, these forces, and predicted that these things would exist, but no one's ever seen them before. That was one of the really cool things. Remember at the beginning of class, I kind of talked about it at the beginning of class last time, that quantum mechanics came up as an explanation for unsolvable experimental problems, things that we observe that are unexplainable. And so quantum mechanics comes up as a way to solve those problems. In the case of these fundamental forces, we predicted the theory before we ever saw any experimental result. It's the opposite effect. Right? The prediction came first, and then the experiment happened. It's the other way around, which I think is very interesting. It also tells you something about the power of the theory. Right? We came up with quantum mechanics, and by using that, we were able to predict that these things exist, and then we go into the lab and predict them. Right? That's the ultimate goal for a scientific theory, is that it's so powerful you can predict things you've never seen before. Interestingly, something that you should consider is that if you take a particle, if you take a system and excite and heat it up very, very hot. So imagine you have an atom, right, that is heated to 10 to the 15 Kelvin, which in energy turns out to be 2.37 times 10 to the 13 kilojoules per mole. Imagine you heat an atom up to this insanely high temperature. People have done this before. Certainly gotten temperatures this high. At this temperature, electromagnetism and the weak force become one. Interestingly, this is kind of an amazing part about physics, is that as you cool, as you get hotter and hotter, let's go the other way. As you get hotter and hotter and hotter, things start to blend together and you can't tell them apart anymore. And it's so extreme that once you get to this certain energy, the difference between the electromagnetic force, which you know and love, it's the whole reason why we can see anything here, why chemistry exists, and the weak force, and I'll talk a little bit about what the weak force is in a second, also relevant for chemistry, they become one. There's no difference between the two. They become an identical theory. Right? And this was called electroweak unification, happened in the 1970s. They discovered this. And what happens is that the difference between a photon and the force carrier for electromagnetism, photon and these bosons, very different particles. These are heavy, massive particles. The photon has no mass at all. Right? It's massless. They become the same thing. They mix together. And they become indistinguishable. Become like a doublet, if you will. They're kind of a combined. It's like they both come together, and the net is a particle that's part photon and part boson. Part massless, part massive. Right? And this happens at high energy. People have been able to observe this. Right? This is why they build particle accelerators. Particle accelerators can create energies this high. And I can explain why that is. But one of the things that you should remember is that at these high energies, imagine that you want to collide two particles together so that their collision has this much energy. Right? At these high energies, mass and energy are the same thing. Right? That's what Einstein tells us. In order for two particles to have that much energy in a collision, you have to accelerate them to near the speed of light. And Einstein tells us that near the speed of light, energy is the same as mass. Okay? So often, when you go look at particle physics results, and you look at the masses of particles, they report them in energy units. And that's because the mass and energy aren't any different to each other. Right? They're identical by relativity. And so typically, masses are reported in units of electron volts, eV, where, I have the conversion here just a second, where this energy, right, this energy, 2.37 times 10 to the 13 kilojoules per mole, is approximately 246 giga electron volts, GeV. Okay, so when you look at physics papers and they look at masses, they're always reported in giga electron volts. And this is the energy that, for them to discover a particle, like for instance, the Higgs boson. If you remember a couple years ago, this God particle thing that they talked about, they built a big LHC in Switzerland to build it, to detect it. And they found the Higgs boson, and they said it had a mass of 125 giga electron volts. You go look on Wikipedia for the Higgs mass, that's what it reports. And that's what this is. That's what this number is. Okay, so it's a mass. We report it as an energy because energy and mass are the same thing at very, very high speeds, at relativistic speeds. So just as a point of comparison, the mass of the proton, which we call P+, is 938 mega electron volts. Okay? Right, but that's quite a bit lower energy than where the electromagnetic and the weak force unify. Right? This is 3 orders of magnitude higher, right? Mega to giga. Right? And of course, in terms of AMU, this is 1.007 AMU. Right? So when you think about when you think about a proton, you know a proton has roughly a mass of 1, right? Like a hydrogen atom, right? Hydrogen atom is basically just a proton in terms of mass. So it's 1.007. So that means that the Higgs boson, the thing that they detected back in 2012, about 10 years ago, it's 125 giga-electron volts. Right, what does that mean? Well, that means that the particle is roughly, if you were to weigh it, you can't weigh it, but if you could, would be on the order of, what would that be? So if this is 1, it's about a giga-electron volt. It's about 130 AMU. It's about the size of a molecule. Right? But of course, the difference between mass, that's when we're thinking about chemistry, where we're not going at the speed of light, where energy and mass are very different things. Right? But if we were able to slow the Higgs boson down, cool it down like you could touch it, which of course is impossible, it's very unstable. It only exists for about, I can't even imagine, 10 to the minus 18 seconds, a tiny amount of time, an attosecond, less than an attosecond. So it lasts for a very short amount of time. But if we were allowed to hold it and have a mole of them, then it would be a mole roughly of a molecule. That's really amazing how big these things are. But again, you don't ever think about them having masses because energy and mass at high speeds, relativistic speeds, are exactly the same thing. Right? There's no difference between energy and mass. And that's a really kind of interesting thing about subatomic world, is that once you get to chemistry kind of is the limit before you get to E equals mc squared. Right? Very little in chemistry relies on this. There are some atoms that require you to think about relativity. But when it comes to carbon, nitrogen, oxygen, hydrogen, the atoms you love and exist with, we don't ever have to worry about this. So the difference between mass and energy is completely distinct. We don't have to worry about that. So in some ways, that's really cool, that chemistry is very fine-tuned to be at this point where these kind of fundamental forces become strong, right? Strong force holds our nuclei together. The weak force helps, the reason why the weak force is so small helps prevent atoms from falling apart. So the strong force keeps them together, and the weakness of the weak force keeps them together for longer. And we happen to be right in the region where the electromagnetism is really strong, right? So chemistry as we know it, the physics, the way that we would define physics in a chemistry class, chemical physics, so the physics or chemistry, let's just say chemistry from the point of view of this physics, is the physics of systems where the electromagnetic force dominates. Think about everything that happens in chemistry. Exchange of electrons. Putting nuclei together with electrons around them, right? It's all electromagnetism, right? So chemistry is just the physics of electromagnetism, right? The particles that interact strongly electromagnetically are the ones that define chemistry. All right? So these are the forces. So let's talk about the particles. All right? There are many different particles. But I'll talk about the most important ones. Different types. Particles come in different classes. All right? Not all particles are the same, obviously, and some are very different than others. So one type of particles are called fermions. Now, as we'll learn, particles have something called spin. Right? They have this intrinsic angular minimum, this intrinsic ability to spin forever and ever. They have an angular minimum associated called spin. Electron has a spin of 1/2. Right? The fact that it has the proton has a spin of 1/2, which is what enables us to do NMR on. So fermions are particles that have fractional spin. I will define spin soon, but think of it as just something that's associated with a particle, like a charge. All right? Particles have charges and they have spins. And so fractional spin. So for example, the electron is a fermion. The electron spin is 1/2. Right? It's 1/2. There's a very, very important consequence. Two fermions cannot exist in the same space in the same state and in the same state. What this means is that, not surprisingly, if you take an electron and bring it closer to another one, you can't put them on top of each other. It's physically impossible for them to stand on top of the same point. They can't exist in the same space, right? One, they repel each other, but even if you could beat that repulsion, they can't exist in the same space. All right, and that's a rule. Any fermion, all fermions, any particle of fractional spin, you can't have two or more fermions together in the same space in the same state. Okay, so you can't have two identical electrons sitting right on top of each other. Okay, if you remember in general chemistry, you might have learned Pauli exclusion, right? In Pauli exclusion, each orbital in your atom gets filled up with a spin up and a spin down electron, right? You don't have two spin ups and two spin downs, so you have an up and down. Those are the only two possible states. That's the plus 1/2 and the minus 1/2. And you can pair them up that way, but you can't put two 1 plus 1/2s together. Right? They repel each other and they don't exist in the same space. Right? All fermions are like that. There are other types of fermions. And we'll talk about them. Okay, but electrons are the most obvious example of them. There are also particles called bosons. Now bosons are different. They are particles with integer spin. Some examples. Some of you know maybe know and love are photons, light particles. They have spin of 1. Another example are the gluons. Right, that's the weak force. And the WZ bosons, those are the weak force, or these are the gluons are the strong force, sorry. WZ are the weak force, and so on and so forth. What this means is that the bosons have the opposite property as fermions. Any number of identical bosons can exist in the same space. Right? There are lots of really cool experiments that show this. There are certain atoms that are bosons. Certain types of rubidium and sodium atoms are bosons. Nitrogen 14 is a boson. And what that means is actually, so what you can do, if you can cool, for instance, a gaseous rubidium atom cold enough, it will condense into a new phase called a Bose-Einstein condensate, which you may have heard of before. And what Bose-Einstein condensate is a very, very low energy phase where all of the rubidium atoms exist in one space together. It's a collective unit. All right. So instead of having individual rubidium atoms, you have one confined material, one coexisting space that's consumed identically by identical rubidium atoms. They're all in the same region, space, sitting on top of each other, literally. Right? Which is very cool. Right? You wouldn't expect that these atoms are physical objects, right? But it turns out because they're bosons, you can stick them together and you can force them all really close together in such a way that you can't with electrons. They don't have that ability to push themselves away like fermions do. So you can slam bosons together. That might make sense of light, right? You're getting a stream of photons. Imagine you have multiple, lots of really bright lights. That's basically the same concept of having all these light particles hitting you simultaneously, right? When your lights are really bright. As you turn the brightness up, that means more photons are leaving simultaneously from the surface, right? It's becoming brighter, right? They just sit on top of each other. Okay, so all particles can fall into these two categories. Right? Every particle, every atom, every electron, every nucleon, everything is either a fermion or a boson. All right? And they have very different physics and different applications, of course. There are different types of fermions. There's some called quarks. These are fermions that interact via the strong force and come in pairs. Let me show you, or in groups. Quarks, you can't have a single quark. You always have at least a pair. Sometimes you can have trios, sometimes you can have 4 quarks together, but they never come separately. And interestingly, these make up the proton and the neutron. The proton is 2 what are called up quarks plus 1 down quark. I'll talk what those are in a second. And the neutron is the opposite. 1 up quark plus 2 down quarks. All right, so the proton and the neutron aren't fundamental particles. They're composite. They're a sum of 3 particles. And these have even weirder characteristics than any of the ones we've seen before. There are 6 different quarks. They have different masses. And how you combine them leads to different types of particles. And what we'll show is that the proton is the ground state combination of quarks. It's the lowest energy combination of quarks. And the neutron isn't. It's what's called an excited state, which means it can decay. The neutron is not stable. If you take a neutron by itself, it falls apart within about 30 minutes. A proton, however, it's the ground state. There's no way it can decay. Stable indefinitely. Here's the interesting thing about physics in this realm. And I'll explain what the quarks are in just a second, but just a step away. The fact that E equals mc squared changes everything. Energy and mass are precisely the same thing. So when we're in chemistry, where E isn't equal to mc squared, we often think of mass and energy as being 2 different things, right? A particle with mass has different energy levels, right? An atom, for instance, has a mass, and it has different orbitals, right? The 1s orbital, the 2s orbital, and so on. Those are different energies. At relativistic speeds, where E equals mc squared is true, there's no difference between energy and mass. So the idea of an orbital and an atom is the same idea as an excited particle, a particle of a larger mass. So a proton is somewhat, if you take 3 quarks together, the proton is the lowest energy state of 3 quarks. It's like a ground state, just like you have in chemistry. It's the 1s orbital of the these are called hadrons, these composite particles, hadrons. This is the ground state. It's the 1s orbital, if you will, of the hadrons. So it can't decay to anything, right? It's the lowest energy state. That's why the proton exists forever. No one's ever seen a proton decay. But the neutron is an excited state, slightly larger in mass, as I'll show you, and therefore it's in a higher energy state, which means it can decay, and it does. If you pull a neutron away from an atom by itself, the half-life is about 30 minutes. Neutrons don't last very long. Okay, and there are 6 quarks, and I'll show you what I mean by these energy states. Right, that particles are just energies. There are 6 quarks, so I'm going to draw a table. Oh, that's not a good 6-member table. Here we go. Okay, and I'm going to put their spin in the top left and their charge. Right, that's their electrical charge. Just like this, the electron has a charge of -1 as well. So there's the up quark, and I'll put their mass at the top. There's right, this is the periodic table of the nuclei, if you will. So they have a spin of 1/2. And interestingly, the up quark has a charge of 2/3. It's weird, isn't it? Right? It doesn't have an integer charge like an electron. Electron has a -1 charge, right? These have fractional charges. Very strange. There's also what's called the charm quark. See. Notice that it has the same spin and the same charge. There's the top quark. Notice it has the same spin and the same charge. And then there's the down quark. Notice it has the same spin, but the opposite charge. Strange. Notice it has a 1/2 spin. But it has a -1/3 charge. That's new. And there's what's called the bottom quark. It used to be called beauty, but now it's called bottom. It also has a -1/3 charge and a 1/2 spin. And then the masses, this is 2.2 millielectron volts, very small. The charm is 1.28 gigaelectron volts, very big. This one's 170, the top, this is top, sorry. It's 171.3.1 mega electron volts, so about the size of a proton. The down quark has a small mass of 4.7 millielectron volts. The strange has 96 mega electron volts, and the top is 4.18 gigaelectron volts. Right. So there's there's two really small ones, up and down, and then there's a set of the strange in the top that are slightly larger, slightly higher energy. Right. They have bigger masses, and then there's two that are much higher in energy. Not surprisingly, it took them the longest to find these two. Bottom wasn't discovered until 20 years after up and down were discovered. And that's because it has higher energy, which means it's more unstable. Right? It's the idea of energy and mass are the same thing. So the idea that as a particle gets more massive, that's the equivalent of an energy state in an atom, for instance, of higher energy. Right? Mass and energy are the same thing at this level. So there's six of them. And if we notice, the proton is 2 up quarks and 1 down quark. Well, that's 4.4 plus 4.7. That's roughly, if we just add them together, just roughly, that's 4.4 plus 4.7, which is 9.1 mega electron volts in mass. And the neutron is 1 up, 2.2 plus 2 times 4.7. So that's 4.7 is 9.4, which is 11.6 mega electron volts, right? So the neutron's heavier than the proton, and therefore it's higher energy. Therefore the neutron turns out to be less stable than the proton. It falls apart. The proton is the lowest combination of 3 quarks on this table. Lowest combination, therefore it's the lowest energy. It's the lightest particle, and it's also the most stable. So particles that are compositions of multiple particles, quarks or leptons, I'll just call them quarks. We haven't introduced leptons yet. Quarks are called hadrons. Right? They're not fundamental particles. Protons and neutrons aren't fundamental particles. They're combinations of fundamental particles. Right? Quarks are fundamental. There's nothing, you can't subdivide a quark into a smaller particle, is what I mean. Right? This is the smallest you can subdivide it to. So a proton and a neutron is not a fundamental particle, it's a combination of fundamental particles. Okay, and so, and just as a note, quarks interact primarily through the strong force, the nuclear force. Right? The strong force used to be called the nuclear force because it was what was understood that kept the nuclei together. Right? This attraction between quarks or hadrons. Right? That's what they call the nuclear force. So they primarily interact with the strong force, but they also interact using weak force, and I'll show you how, and electromagnetic. Right? They're, as we know, they're the same thing, weak and electromagnetic. So if it interacts with the weak, it probably interacts with the electromagnetic force too. Okay, so quarks are what keep atoms together. They're what build nuclei together. And their forces, the strong forces, are what keep nuclei together. Okay? Right, so the strong force is what builds up nuclei. And the electromagnetic force is what sticks electrons to them. Okay? There's one more type of fermion that I want to talk about. There's also what are called leptons. Fermions that do not interact via strong force. This is like the electron. Electron is just the electromagnetic force. Okay. So just like a quark, an electron is a fundamental particle, right? You can't subdivide an electron into smaller particles by itself. It's just like a quark. It's a fermion just like a quark. They both have spin 1/2. Electron has a charge of -1 and spin of 1/2. But it doesn't interact with the strong force. It only interacts with the electronic force, right? So there's something slightly different between a quark and an electron, right? They're different, even though they have similar characteristics. Their charge, their spin, they're both fermions. That one interacts with the strong force and some don't. And I don't really understand the reason why that is. It just does. Is there some of these things, it's funny, standard models, the thing that describes this theory. A lot of this has been created empirically. Sometimes things get calculated with an expectation that they know the answer. Some things get calculated without an expectation they know the answer. And so sometimes these things get described and understood, and there's no real good reason for them because the theory doesn't describe it. It just is what it is. And I don't really understand the difference why quarks interact but leptons don't. There's just particles that interact with the strong force and some that don't. There's a lot of unsolved mysteries. There's other ones. Another place where leptons interact is in the weak force. And the classic example of the weak force is this. Carbon-14 dating, carbon dating. So again, you might know that the way that they measure, often one of the common ways they measure fossils is by taking carbon-14, right, and measuring the abundance of carbon-14 in the material. Carbon-14 decays through the weak force, through what's called a beta decay. And what that is that carbon-14 turns into carbon-nitrogen-14 by releasing an electron, and also releasing a new weakly particle called a neutrino. What is a neutrino? We haven't mentioned this. A neutrino is also a lepton. It's a fermion. It has spin 1/2, but it has zero charge. And therefore interacts very weakly with everything. So the neutrino is a tracer for the weak force. Right? Weak processes like the decay of carbon-14 release a neutrino. But the charge is 0, has no charge, it doesn't interact with the electromagnetic field. Right? There's no charge, it's just neutral. And has a mass of approximately 0.120 eV. Tiny, tiny mass. It's a tiny, tiny particle. It barely interacts with anything. But they get released, and not only do they get released a lot. Right? The assumption is that the Earth sees something like 10 to the 20 to 10 to the 30, maybe it's even more than that. Maybe it's closer to 10 to the 50 neutrinos every second go through the Earth from space. And what they do, and not a lot of people understood whether neutrinos have to exist physically, but it was very hard to detect them for a long time. And so they built these giant detectors underground. There's one in Antarctica. There's one in Japan that's built in a giant cave. There's a couple of others around the world where they have this. Basically, it's a super effective detector of neutrinos. They fill it with water, and they look for certain types of radiation that occur when neutrinos interact with particles in the water. Okay. They look for very, very small signals. And so they have these giant detectors. These giant detectors theoretically absorb 10 to the 30 particles a year, maybe more. And it's a good year when they maybe detect 17. Right? So they know that the flux of neutrinos is on the order of 10 to the 30, but they might only actually have positive detection of about 100 or less. Right? They interact very weakly because the charge is 0, so it doesn't interact with an electron. Right? Electron doesn't even know this exists because it has no charge. It has a tiny mass, which means it's super low energy. It doesn't do anything when you collide it with anything. So it's very hard to detect. But we know there are millions, an astronomical amount of neutrinos in the world, or in the galaxy, in the universe, being moved around constantly. But to be able to detect them is near impossible. Okay, and it was just recently that people have been started to detect them, but not only that, there are 3 forms of neutrinos that interconvert rapidly. There are 3 different, just like there are 6 quarks, there are 3 different neutrinos. But once a quark is a quark, it can't really change to another one, mainly because they come as pairs. But a neutrino can oscillate between the 3 forms rapidly, which is crazy, right? So there's all this new physics associated with it. We don't really understand why that happens. But a neutrino is not only one particle, but it's 3 particles, and it's not entirely clear depending on which particle it is. They all have different characteristics, and the particle itself can change its form as it wants, which is absurd. Right? So it's a very crazy thing. But it's the most common particle. In some ways, it's the most common particle in the entire universe. There are more neutrinos than there are anything, maybe other than photons, other than light particles. But we understand they're very important. But they are super important. So this is how we know that the weak force exists, often is because of the detection of neutrinos. Right? The weak force is what generates them. Okay, well, how much time do I have left? This is 4:15. Okay, I got a little time left. Good. All right, so I want to finish up with two more points. I've given you a giant zoo of particles today. And I want to finish up today, talking about where we sit. And I kind of gave you the hint that chemistry is electromagnetism. There's no difference between the two. Electromagnetism predicts chemistry. Chemistry can only exist because of electromagnetism. Therefore, we only consider protons, neutrons, and electrons. The other particles don't exist, to our view. They don't exist because we're not at high enough energy. Once you get to low enough energy, right? Once energy is on the order of room temperature, or colder, right? Where we sit now, quarks only exist as protons and neutrons, right? So we don't even have to worry about other combinations of quarks that are them by themselves, because it's so cold that they come back together and they come to their lowest energy state, which is a proton. So only protons exist. And neutrons can't exist by themselves. They only exist next to a proton. Neutrons are only stable in the presence of protons. And there's a lot of reasons why that is. But in some ways, protons and electrons are the only things that are stable in the universe. So the only two things. Neutrons, of course, are important. But neutrons can't exist without protons. They can't exist simultaneously. They have to exist simultaneously. So much of our chemistry is driven by protons and electrons because they're the only two things that are stable at low temperatures. Right? Everything else kind of decays into these two things, or light. And so therefore, chemistry is basically just reliant on these two particles, protons and electrons. They're the things that drive chemistry. Protons give you the positive charge, electrons give you the negative charge. And that's electromagnetism, right, in its whole. Exactly, electromagnetism. What I'm going to introduce on Wednesday, and so what we'll do throughout this class is, so let me write this down. Our ingredient list for chemistry. Electrons. Just as a reminder, electrons have mass, -1 charge, and +1/2 spin. Right, that means they're fermions. We have protons. They have their massive +1 charge and +1/2 spin. Those are -1/2 spin. They're also fermions. Right? Imagine if protons were bosons, then a nucleus would just be a conglomeration of protons sitting on top of each other. Right? You wouldn't have atoms. Right? So it's important that they're fermions. That's the whole reason why atoms exist. If they weren't made out of fermions, chemistry and life wouldn't exist as we know it. Right? The fact that they can't sit on the same spot at the same time in the same state is the entire reason why we exist. Neutrons are less important, massive, zero charge, unstable, and +1/2, -1/2 spin. Notice all the fundamental building blocks are fermions. And then there's finally one more particle, right? These are particles all interact via the electromagnetic force, well, except for neutrons. Just strong force. Right, they're what hold the nucleus together. Right, the neutrons are kind of the glue that hold protons together. And there's one more particle, the force carrier, the photon, light particle, light itself. Right, you can't have electromagnetism without light. They're one and the same. They describe, right, they're two sides of the same coin. Electrons, protons, they all interact through light. So that is our electric EM. It has zero mass, right? Light has no mass. It has a spin of 1 and zero charge. Right? Here's an interesting point. All particles with no mass move only at the speed of light. Okay? There are other massive particles. You don't really need to worry about them. The photon's the most important one. Moves at the speed of light, right? That's the whole point. It can only move at the speed of light. The only way to change the speed of a photon is to change the speed of light, right? For instance, the speed of light in water is different than it is in a vacuum, right? The only way to slow a photon down is to make the material less susceptible to photons, make it slower. All particles move at only the speed of light. No, and by definition, no massive particle can move at the speed of light. Right? So the only thing that can move at the speed of light is a photon, effectively. Not surprising, right? The speed of light can only be driven at the speed of light by light itself. Okay, these are our ingredients for chemistry, right? Protons and neutrons come together to make strong force-held nuclei that have lots of positive charge, right? You're adding neutrons, zero charge to a bunch of +1s. The electrons cancel that charge out. And the thing that allows us to communicate energy from one chemical molecule to another, or within the molecule or the atom or whatever, itself are the photons. Photons are the way we talk to each other in chemistry. It's how we transmit energy. It's how we communicate with atoms and molecules. Right? And that's why spectroscopy is so powerful for chemistry, because all of the interactions in chemistry are mediated by a photon. All electromagnetic interactions are mediated by photons. So what's a natural way to probe chemical changes? Well, to use light. Right? Can't have one without the other. So photons is our best friend. Right? We're going to use it to our advantage. And what we'll also learn is that the physics of these things all relate to each other. And we can use this idea of photons as a wave and a particle in the same way that we can talk about electrons as a wave and a particle. Talk more about that this week. All right, that was a lot. Any questions from anybody? Again, I really spread out very far through physics, and then I really want to narrow down to why chemistry is what it is, and why we really don't have to worry about all of these exotic particles in chemistry, because we're not at the energies we need to worry about these things. We only look at the things that exist at low energy, which are these four. Everything else disappears, right? Which is very natural, right? That's why chemistry is so cool to me, is that in some ways that the universe is explicitly constructed, or happen to be, depends on how you look at it, to have chemistry happen at low energy and at regular temperatures. Right? We would, if we didn't have all these things come together perfectly, we wouldn't have chemistry. Right? If one of these numbers change, everything changes. Okay, so the last thing I want to talk about is scale. The scale of chemistry. Right? And this is related to energy. There is one number in this class. And I'll talk about where that number comes from and how it was measured on Wednesday. But there's one equation that defines everything in this class. It's that energy can be related to a frequency or a wavelength. So if we multiply the frequency by this number h, this is the constant, we can convert between energy and frequency of a wave. This is also equivalent to h times the speed of light divided by the wavelength. Right? This is the speed of light. And this is the wavelength. Right? This is very natural, right? We know that the energy in chemistry is associated with waves, with photons, right? Light. Light is a wave. So this is a particle, of course. We talked about it having a mass and a charge, but it's also a wave. We know it as a wave. Okay? It's the way it's traditionally understood as a wave. Light is a wave. Right? So it has an intrinsic wavelength or intrinsic frequency, however you want to think about it. And what you learn at the beginning, what we'll learn on Wednesday, is that there's a way to relate that to the energy of the system at the scale of chemistry. E equals h nu. Okay? This constant, this is actually a law. This is called Planck's law. And the number h is well known, and it is a fundamental constant. If you remember the gas constant from last semester, we used R all the time. In this class, we're going to be using H all the time. H is our fundamental relationship between energy and another measurement of energy. Right? And thermo, R converts temperature to energy, right? And quantum, H converts wavelength or frequency to energy. Interesting. Notice that this is time, right? You remember last semester, my first lecture, I talked about how energy is a function of time. Right? Energy is due to the fact that we have time. Right? Time and energy are the same thing. They're dual to each other. Right? We see that again. That in quantum mechanics, or in this class in chemistry, we can relate energy to time. Right? The time of something happening is equivalent to energy by this formula. We have a frequency of something happening. Imagine a bond vibrating. Some frequency of how fast it vibrates, that'll tell us what the energy is. And the conversion factor is H. And H is called Planck's constant. And H is defined as 6.62607,004 times 10 to the minus 34 joule seconds. It's a small number, very small number. So the question is think about it this way. If you multiply this by a rate, right? So let's think of something that happens once a second. All right? Imagine you have something in chemistry that happens once a second, an oscillation, like a vibration or something like that. If you multiply this by 1 per 1 second, the amount of energy that process must have is 1 times this number, 10 to the minus 34 joules. Multiply the s's together, the seconds together, they go away, and you're left with joules. Right, so this set tells you that if you're able to measure spectroscopically something that's respective of a process, like a bond vibrating in infrared spectroscopy, if the bond vibrates, you're going to observe a wave associated with that in frequency, right? Or wavelength, however you want to measure it. I guess you measure wavelength in infrared spectroscopy, inverse wavelength. And that gives you an energy. Right? It gives you an energy that you can measure, that you can feel, and that you can think about in terms of temperature or whatever. Right? The natural classical energy. Right? So this is really interesting, and we'll talk more about why this is so revolutionary. This concept that a wave contains energy, and its energy content is only due to its frequency or its wavelength. We'll talk more about waves on Wednesday, but that's the idea. And this constant comes up everywhere. In fact, the way that we can define chemistry is the physics of systems where H is large relative to the scale of the system. Let me talk what I mean by that. Let's imagine that we have a molecule like this. Methane. Okay? And we're interested in the vibration of this bond. CH, how strong is that bond? Okay? And you go take an infrared spectrum of it. How strong is this bond? And you see the CH stretch at 3,000 wave numbers. Right? This is equal to 1 over the wavelength. Okay? By definition. Okay? Get the infrared. Right? We can plug that in. Equals hc over lambda, right? Equals h nu. Equal to 3,000. Oh, sorry, I gotta multiply it by a factor of c times 1 over the wavelength, right? And that's our number here. So h is 6.626 times 10 to the minus 34 joule seconds. The speed of light is 299,792,458 meters per second. We'll simplify this a little bit. And 1 over lambda is 3,000 wave numbers, which is going to be 3,000 centimeters. Inverse centimeters is how many inverse meters? 30, right? Am I right about that, or am I off by one? So let's convert that. 1 cm. How many centimeters are in a meter? 100? Yeah, so that's going to be 3,000 divided by 100. Yeah, so 3 meters, 3 inverse meters. Okay? And so that's how much energy this stretch has. And so let's simplify this a little bit. This is 6 times 10 to the minus 34 times 3 times 10 to the 8 times 3, right? And our units are, so the seconds cancel out, the meters cancel out, we're left with joules. Exactly what we want. 6 times 3 is 24. 8 plus minus 34 plus 8 is 26. So that's 24 to the 10 to the minus 26. So that's 2.4 times 10 to the minus 23rd times 3, which is joules. Which is, let's just say roughly it's 9 times 10 to the minus 23 joules. Well, if you multiply this by Avogadro's number, now you have a mole of bonds. 6.02 times 10 to the 23rd, right? So now you have a mole of molecules. Well, how much energy do you have? Well, look, they cancel out, and you're on the order of 54 joules per mole. Doesn't that number seem chemical to you? Right? Low energy. Right? So the idea is that chemistry occurs on the energy time scale, the molar energy scale of 1 to 1 joule to 1 kilojoule. Let's say, on the order of 1 joule or 100 joules. Let's say 1 kilojoule per mole, which is the chemical time unit scale, right? Everything in chemistry can be expressed in terms of kilojoules per mole, right? And so chemistry, right, if we think about bond energies tend to be on the order of hundreds of kilojoules per mole. So you can imagine if it cost about a little less than 50 joules to stretch a bond, to break it, it might be 20 times that, and now you're getting on the order of a couple kilojoules to tens to hundreds of kilojoules. Right? And so chemistry occurs that when you multiply H, well, chemistry is where H times the Avogadro's number times 1 second is on the order of 1 joule times delta T. Let's just say time. Whatever the time scale is. All right, so that means then that H, in some ways, in our chemical time scale is on the order of 1. Right? And so chemistry happens where H is dominant. Right? So things where H is very small. So for instance, your car, for instance, right? Your car generates multiple kilojoules, not per mole of cars, but just one car, multiple kilojoules of itself. That's a ton of energy compared to H, which for 1 second is about 10 to the minus 34 joules, right? So H is very, very, very small number on an energetic time scale. But when you shrink yourself down to chemistry, you realize that chemistry happens where H is kind of on the order of 1 in terms of energy. Right? So where H is roughly unity. So Planck's constant determines what scale chemistry occurs at. So chemistry ends up being energy 1 joule per mole. Right? Length turns out to be around 10 to the minus 10 meters in angstrom. And time, 10 to the minus 10 seconds, which is about 100 picoseconds. Right? Everything we study in chemistry, the length of things, the energy that it takes for chemical processes to occur, and the time at which things occur, all tend to fall in this range. Right? And that's because H, the size of H, determines where that happens. Right? Chemistry is the processes of things that occur at 1 joule per mole, tend to be on a length scale of about an angstrom or a nanometer, and tend to occur kind of on a very fast time scale, about a nanosecond or so. That's chemistry, and that's where H times Avogadro's number tends to be about 1. Okay? And so H determines the scale of chemistry, what size it occurs, and how strong chemical events are. ultimately set by this number. This number determines it. Okay? So the stuff about nuclei, right? Protons and stuff. That's at very, very high energies, right? I showed you that the electromagnetic and the weak forces unify at something like 10 to the 13 joules per mole, right? That kind of physics exists in an entirely different world, multiple orders of magnitude from chemistry. But at the same time, this energy is very, very small compared to gravitational energies, right? The energy of attraction between the Earth and the Sun is, in terms of energy, in terms of potential energy, is an ungodly amount of joules. I mean, I can't even imagine how many joules it is. I'd have to think about it. But it's 10 to the 8, 10 to the 9 joules, right? So chemistry occurs at a much, much smaller scale than gravity, but a much, much bigger scale than the strong force, for instance, and the forces that pull our nuclei together. Right? There's a very big different scale. There's a huge scale difference from the strongest forces to the weakest forces in the world. Something like 200 orders of magnitude between the strongest gravitational forces and the weakest and the smallest attractions at the smallest scale. It's about 150 orders of magnitude. So chemistry is just right in the middle. Chemistry is perfectly right in the middle. It's not too big, it's not too small. It's right in the middle. Okay? And that's not a surprise. And it depends on who you ask. Some people would say the reason why chemistry exists the way it does is because it was tuned that way. Right? That it can't be a coincidence that everything works out this perfectly. That chemistry happens where the scale, once you think about the constant, is on the order of 1. Right? This idea of unity, where chemistry happens at this scale. Some people think that's a tuned number, and some people think the only reason why we observe that is because that's the only universe we live in. Right? Imagine a universe where these numbers are different. Well, we can't because we wouldn't exist in that universe. Our existence is predicated on the fact that this is valid. Right? Life would be completely different in another universe. So there's different ways to look at it. I assume it probably comes down to religion, how you want to think about it, whether you think that our universe is fine-tuned or we just got really lucky. But there's a lot of things that say we get really, really lucky. Right? If these numbers were any different, chemistry wouldn't exist the way we understand it. If H were 10 times larger, none of us would be here today. In fact, there would be if H were 10 times larger than it is, there would be no matter in the universe at all. So things are very perfect, perfectly aligned for us to discuss this. So it's important to think about that and keep that in mind, that things are very fine-tuned, that chemistry occurs at the electromagnetic scale just because everything works out perfectly that way. And there's really no explanation why that is. It just is. Okay, that's all I have for you today. So on Wednesday we'll get started with some actual kind of quantum mechanics. We'll talk about some historical aspects and try to really pin down what it means to be microscopic. Okay, what happens at the microscopic level? Right, at the chemical level, and then we'll really get into the nitty-gritty very soon. Okay, everybody, have a nice day. I'll probably have